Okay, so just before the lunch, I arrived at the static limit Lagrangian for the HQET. This is the Lagrangian I wrote. This is the part that we got from the propagator that Dirac propagator that I expanded using this heavy quark momentum expansion. And the interesting thing for this static limit Lagrangian is that you do not see any spin-dependent term here. Okay, there is no heavy quark spin-dependent term. There is no flavor-dependent term corresponding to the heavy quark mass. So, for example, you know that the charm mass is roughly 1.5 GeV. Obviously, this is some scale-dependent quantity. Take it as pole mass, let's say. Then the bottom pole mass is pole mass scheme. Bottom pole mass is roughly 5 GeV. And in this, whereas in QCD Lagrangian, there is a heavy quark mass dependent term, which appears as the mass term. But in this HQET Lagrangian, you do not see any dependence on the mass right now. And therefore, this static Lagrangian is equally valid for both D mesons and B meson describing their properties. It also do not have any spin dependence, so there is the heavy quark spin symmetry, which means the heavy quark spin is conserved. And one way you see that is if you define an operator for the heavy quark spin. So, yeah. Exactly. No, not now. Yeah. I have not. So this H nu, as you recall, please recall that this H nu was satisfying this projector 1 plus V slash by 2 HV. And this 1 plus V slash is only picking up the particle component. I could have written an analogous Lagrangian where I only have the antiparticle into my picture. Because my D meson is made of one charm quark, so I'm describing the system with one charm quark. I'm not describing the system of CC bar right now. The CC bar will come probably in the next lecture. So if I define a generator for the heavy quark spin, so this is my SU2 generator. Where this spin operator is just given by the Pauli matrices. Or if you like it, it can be written in terms of the Dirac gamma matrices in hadron rest frame. There is also an expression in with finite velocity. So it also is written as gamma 5 V slash EI slash, where hadron rest frame corresponds to 1, 0, 0, 0. And this EI is orthonormal vector, satisfies the condition E dot V equals to 0. So I'm defining a set of EI polarization vectors which are orthonormal to my velocity. But let us work with this case. This is easier to see. What you can show is that under infinitesimal rotation, so yeah. So this will generate my infinitesimal rotations. So let me write it down maybe. Just give me a minute. So under infinitesimal rotations, epsilon, my field under this generator or this generator would transform as some h nu plus I times epsilon dot SQ dot HV plus order epsilon square. This is my thing that I was talking about. So if I use this expression, basically what we get is 1 plus I epsilon dot S HV. And obviously, the fields HV are Dirac are fermion fields, so they satisfy the usual anti-commutation relations that you have seen in Dirac-Lagrangian. I will not write it down, but that is being used. The anti-commutation relations of HV field is being used. And similarly, the H bar V would transform as 1 minus I epsilon dot S. And immediately, if I substitute my HQET Lagrangian on this HQET Lagrangian, what I would really find is that my HQET Lagrangian transforms to the same Lagrangian plus some order epsilon square. So it is really invariant under the heavy quark spin dependent terms. This particularly this static limit, okay? This is the point. I mean, we will in 10 minutes, we will see there are spin dependent terms that would come out. So the heavy quark symmetry has, as I said, the profound implication of this heavy quark spin symmetry and the flavor symmetry is that, so my HQET, so observation, I have SU2 cross UNF heavy quark, spin flavor symmetry. Which is symmetry of HQET, but not of QCD. Okay. So this is an emergent symmetry of HQET, which is absent in QCD. So the implication that we see of such terms, so just note that any spin-dependent term will appear at order 1 over m. So my implication of this is that I can so, okay. So let's maybe not skip it and then just let me keep, yeah. So my hadron mass, so my hadron is D star, D star or D star or BB star or ones with strange mesons or ones with P wave mesons or anything, is MQ plus some lambda bar associated with the soup of the light quark plus some order 1 over m term that I have not described till now to you. And immediately what we will see is that, so MB star minus MB, so let me just, so this is effective mass of, so light degrees of freedom in heavy light system. You should note that if my mass, the heavy quark mass is scheme dependent, this means this is also scheme dependent. Any other terms that would appear up is scheme dependent, but anything on the left-hand side is scheme independent, okay? Because this is associated with the D meson mass that is seen in PDG or B meson mass in PDG. So if you choose one scheme for heavy quark mass, you have to choose the same scheme for any parameters associated coming up in the expansion, like lambda bar or terms that will come up in 1 by m expansion. So this is order lambda QCD square over MB, which implies MB star square minus MB square is order lambda QCD square. And the same thing would hold for MD star minus MD, except you have MC And this implies MD star square minus MD square is order lambda QCD square. And this order lambda QCD square is some constant that comes up as a matching coefficient in the HQT Lagrangian. This is universal, means it's independent of the heavy quark spin and flavor, because all of these terms, as I kept on mentioning, they appear at higher orders in the expansion. So if you, for example, compare with the experimental data, so yeah, so just a bit of digress, sorry. So before showing the experimental data, I need to mention something. So if lambda QCD is order 500 MeV, MC is 1.5 JeV, and MB is 5 JeV, the corrections that we have in HQET, so the corrections are generally of some order lambda QCD over MQ, which is roughly 30% for charm and 10% for bottom, which is just coming from the ratio. So experimentally, what we have seen is MB star 0 square minus MB 0 square is roughly 0.48 JeV square. MD star, MD star plus square, or MD star 0 square minus MD 0 square is roughly 0.55 JeV square. Then you can write also the analogous relation with MB star plus square minus B star plus square is roughly 0.49, and so on. And yeah, so just one for the strange meson. You see all these differences are quite close to each other. In the case of strange, there is this additional strange meson mass that is contributing. In the case of charm and bottom, there is obviously corrections, higher corrections to the charm compared to the bottom. So that is what the difference is. But all of these numbers are within the same order of magnitude that we get from the experiment. So this is really the power of the heavy quark symmetry that we are seeing from the experiment. Yeah.
So this claim that MD square, MD star, lambda QCD square only.
Yeah.
This is because the mass operator that comes at the level of MD that splits the, that's how the power.
Yes, that's how the power counting is. So, exactly.
So your S vector is a number.
The S vector is basically
Number. Each is a number.
Yeah. I mean, this is the generator of my heavy quark spin. Yeah. No, HV is, so this is in the polyspinner. So this is like, I mean, if you want to say number in the terms of polyspinner, so yes, this I mean, HV has some index IJ that would be contracted with this S and X. So HV dagger S HV. Yes, okay. It's still a matrix.
HV is a row in that direction, sorry, a column in that direction, right?
So HV,
That is a row.
so no, so the thing is, HV is like a polyspinner with 2 cross 1. This is, I mean, this is the reason using this, I got rid of the 4. This is, you can think of in terms of, yeah, I mean, if I expand this SI and expand this polyspinner, then I also will have a 4 cross 4 structure. In some sense, my HV is like describing yeah, it's a 4, it's a 4, yes, it's a 4 column in with, okay, sorry, HVS. Yeah, now I'm also, maybe I'll come back to it. Just give me some time. No. So maybe let me come back to this. I'll think about it and I'll try to answer. Sorry. So, so you are correct that. Yeah, HV. Dagger. That's a good question. Did I write? No. It's a valid question. I did. Maybe I'll give me some time. I'll think about it and then answer. Sorry. But maybe you are correct that something on here. Sorry. Okay, so so this is what we see from the experiment, which basically is satisfied from the heavy quark spin symmetry. I just want to define the normalization of the states in heavy quark EFT, because we discussed about the normalization in the case of the scalar field theory yesterday. In this HQET, we have the normalization defined as where V0 is match. If you use this definition and relate it with the relativistic normalization, which is given by H of P, H of K as 2EP two pi cube delta cube P minus K, you see that my H of P, which is in the relativistic theory, is related to square root of 2m or mh h vk plus order 1 over m. So we saw this yesterday in the scalar field theory. So just to summarize the things. Okay, so this was all about the static limit, but the world is not static. Obviously, there are these heavy quark charm masses are finite. Heavy quark masses are finite. Charm has some finite mass. Bottom has also some finite mass, which means there are corrections that has to be accounted for beyond the static limit. And recall the mode expansion that I did yesterday in the case of fermion. So I expanded my Dirac field yesterday that I wrote when I got the polyspinner as e raised to minus IEP. Yes, everybody recall this thing yesterday? In the heavy quark EFT, instead what we do is, what we start with is something analogous. Note that if you have this momentum that I have written, which is working, which is basically, so this momentum P mu, which is MQ V mu plus K mu, This basically tells me that the heavy quark is almost on shell. Plus, there are some corrections of order lambda QCD that is coming from the interactions with the light quarks. And so again, my goal is to extract this part from the Dirac field and write everything in terms of fluctuations around this on-shell conditions of the heavy quark. So I define my Dirac field psi of x as through field redefinition a part that is HV of x, this is the one that you have seen, and a part which is capital HV of x, which will be connected to the fluctuations of the antiparticle in the Dirac field. So this is the mode expansion that you have already seen yesterday. When we did it for the scalar case, we had to multiply with 1 by square root 2m because the derivative in the scalar field theory is two-time derivative, where in the Dirac-Lagrangian it is only one-time derivative. If you did not include this 1 by square root 2m in the scalar case, you would not get the non-relativistic kinetic energy that of p square by 2m type of factor. Here, as we will see, we automatically, because of this one-time derivative, we automatically get something like a non-relativistic kinetic energy term. So you take this so you take this and start with the QCD Lagrangian. Just give me a minute. So you use that here. And let's break up. I'll just write the direct result instead of showing things. I think you can do it. So the results that we get in terms of the fields are h nu bar I v dot d h nu minus h nu bar 2m h nu slash id slash h nu plus id slash h nu. Okay. People can see parts. Okay. So yesterday, if you recall, in the Pauli equation, like when we were getting this Pauli equation, we had this piece 2m when we were writing the equation for the non-relativistic or the antiparticle case. Okay. So in true sense, this HV is the piece of the Dirac-Lagrangian that is describing heavy quark fluctuations around the on-shell condition here. And this piece is HV bar or HV, capital HV is describing the antiparticle fluctuations with mass scale 2m around this on-shell condition. So this is what the whole point is. And if I just use this Lagrangian, I can basically write a field HV a diagram like this, which would go like 1 by MQ order from this heavy quark, from this anti-quark propagator, because of this 1 by 2m factor. So so the point is, the goal is that we eventually want to integrate out this heavy degree of freedom, and which means shrinking this fluctuation of the antiparticle of the scale with the scale 2m, and defining something like a contact interactions with HV and HV. So after integrating out, sorry. So again, I just want to stress that this is antiparticle fluctuations, and this is particle fluctuations. This is because 1 plus V slash by 2 acting on psi Dirac gives me HV, and 1 minus V slash by 2 psi Dirac gives me the capital HV. So this projector picks up the particle, this projector picks up the antiparticle. Note that I'm trying to describe the heavy meson, not the heavy anti-meson. If I have to do the heavy anti-meson, the role of these two fields would be just reversed. You would start describing in the case of heavy anti-meson, heavy antiparticle fluctuations, massless fluctuations, and there the heavy quark fluctuations would scale as 2m. So there is an exercise in the exercise sheet there you will derive HQET Lagrangian for heavy anti-quark based on similar philosophy. So again, if I use my equation of motion for the heavy field or the heavy fluctuation HV, what we get is HV is 1 by d slash perp. I need to define my d slash perp. Sorry, I made a tiny bit of mistake. So just give me an excuse or not. Sorry, I made a tiny bit of mistake here. So d slash perp. Which is equals to 0 di in rest frame. Which, as we saw yesterday, is also like goes like order 1 over m. I mean, I wrote a similar term for the anti-quark case when I derived the polyspin. So now, once we have this equation of motion, we just substitute back into our Lagrangian and replace wherever we have this field with this equation of motion. And is now slash point. So So if you now do a systematic expansion, do a Taylor expansion of this denominator, order by order in 1 over m, what you will get as a first term is a term corresponding to just let me see one time. Yeah. Okay, in order to get this, I just expanded this term. I did nothing else. I just did the Taylor expansion. And the first term, if I just take 2m, this is the term I get. This will be the term I get after expanding this v dot dp's together. You have to play a bit of massage here, and so things are there in my notes. I would leave it. So this term is something like analogous to a term which corresponds to hv bar p square over 2m hv. Okay, if I identify my p with minus I del, this basically accounts for the heavy quark recoil from the interactions with the soft gluon. So and this one is what so is what give me the 1 by m suppressed spin dependent. Now, in the hadron rest frame, again, it will be simpler to see. So I had defined d slash as somewhere I had defined, as d mu minus v mu d, just give me a minute, something's not wrong. Sorry. So in the hadron rest frame, if v mu is 1, 0, 0, 0, so rest frame, I can simplify this term that looks like 1 plus gamma 0 by 2 sigma mu nu f mu nu 1 plus gamma 0 by 2. So this 1 plus gamma 0 is basically coming from this piece. The other 1 plus gamma 0 is coming from this piece. Okay? To something like minus 1 plus gamma 0 by 2 S dot B 1 plus gamma 0 by 2, where Bj is Fjk and so this is my chromomagnetic field. And this is my spin of the heavy quark that I have already defined. So in this, why is this, oh, d square. And d pop square is minus d square in for v mu equals to 1, 0, 0. I leave all these identities for you to derive. So, okay, so is everything clear up to this point? Okay. So, so the Lagrangian that we have in hadron rest frame is this. And this is what you saw yesterday, which gives you the Pauli equation as the equation of motion. Now, something to note, this is the term that gives me difference in mass between D and D star, or B and B star, or is basically what is differentiates between the heavy quarks, I mean, these type of mesons. So ideally in the static limit, D and D star are same, they are spin averaged, but this spin dependent term is what differentiates or creates the spin splitting between the two mesons. Second thing to note is that pair creation and annihilation is forbidden because I do not have any antiparticle into my theory. They have been all integrated out. The fluctuations of the antiparticle have all been gone. I could have, I mean, I do not have any 4 fermion type of interactions here because my system is a system of one heavy quark and light degrees of freedom. There is no analog of like C, there's no analog of C bar into my theory now. Now, all of this is, you should note here is that this way of deriving the HQET Lagrangian, where I try to use this mode expansion and pulling out this, like when I wrote this Dirac field as mqv dot x, that hv plus hv. This is at tree level in the sense that there could be more complicated field redefinitions at order that include higher order in 1 by m corrections. But this is only accounting for the simplest case, and loop calculations can modify this field redefinitions. But for that, we will resort to some sort of a matching or some sort of a matching calculation that we will do in tutorial next week or. Yeah. So here there is no direct answer that I can give you because this is mostly in the bilinear sector that heavy quark Lagrangian is. there may be some complications that would come up like in NRQED, because there you would have more particle scattering. Here it works because we are not looking at higher order scattering. Yeah, still two-body problem. But there is no clean example in a way that I showed you in the scalar field theory. It's a little bit difficult to show here. Okay, just to note that you could write analogous heavy quark EFT for anti-mesons, where your HV is replaced with the heavy anti-quark. Like I told you, this is left up to you to the exercise sheet to derive. Just use similar philosophy to get to the thing. And I mean, we can discuss it if people want. And yeah, the last thing is, again, from this term, as we saw yesterday, the G is 2. The G factor for the fermion is 2. Okay, so there is another method called Oldie Hutu Zen. Tani transformation. This is more sort of used in NRQED derivations, in the sense that you have a Dirac Lagrangian you start with. I mean, we'll not discuss it here. I will just tell you, if you want, you look at the detail in this book. So relativistic quantum mechanics by Franz Gross. So the idea there is that you do a set of unitary transformations. Again, these unitary transformations could be 1 by m dependent transformations. And the goal is that you break the Dirac Lagrangian in terms of block matrices of 2 cross 2, where the one block would correspond to your heavy quark part, another block would correspond to your heavy anti part. And just after you have done the block diagonalizations, you would have a similar Lagrangian that would look like HQT Lagrangian for heavy quark and another piece, and a Lagrangian for heavy anti-quark. So just to make you aware, if people are interested, they should go to this book to check the details. Yeah, G equals to 2, it is all tree level. This is that, like I said, this is tree level calculations. Loop calculations would give you different factors. Okay. So okay, so let me just erase the blackboard. Yeah. I'll come into that. Just give me. So this is tree level calculations. At tree level, the Wilson coefficients are 1. Okay. Maybe next week on Monday, when the tutorial is, we will do a one loop calculations for the CF. But I will demonstrate the tree level matching between QCD and HQET and show you that the Wilson coefficient is really 1. Here it comes just from these field redefinitions, but you can do from the matching calculations. Okay. So just to demonstrate very quickly how, again, the matching calculations are done in this EFT, till now I have been just using field redefinition to define my Lagrangian. So let me write the most general Lagrangian of HQET. And then for simple cases, 1 or 2 cases, we'll do the matching calculation and see what we get. So plus there are terms with the with F mu nu and F mu nu plus light quartz. So you already have, so here now you see I have added the coefficient, Wilson coefficient C2, CF, CD, CS, because in general, the radiative corrections or the loop corrections can modify these coefficients beyond 1. They would be, so C2 is some 1 plus order alpha S correction. CF is also something similar. And yeah, and in general, I mean, I have shown the derivation until here, but this term, if I remember correctly, corresponds to, I believe, the Darwin term in the non-relativistic Lagrangian. But maybe I'll check it again. But just as my memory serves, this is probably the Darwin term that we have seen in, for example, when we compute corrections to hydrogen atom in quantum mechanics. So in general, this is this cross. So you just expand the commutator. It's D cross G, because D is a vector, E is a vector. It's D cross E type of thing, or E cross minus E cross D. It's a short form notation I have just used. Sorry. So to do the matching, so we are doing again tree level matching. Just as a first application. And in order to do the tree level patching, first let us define what are the spinors that can come up, or how to write the spinors in the corresponding theory. So in QCD, for particle, there is this U of P, which is square root of EP plus M by 2 EP. U sigma dot P U EP plus M, which is basically equals to U sigma dot P U by 2M plus order 1 by M expansion. Okay, so now I'm writing in terms of two component spinners. So the U is like 1, 0 or 0, 1 combination. So let's use this notation. This is 1, 0 or 0, 1. Similarly, the other one, which is for antiparticle, the V is let me just write down the expression in P less than M limit is minus sigma dot P V plus order P square over M square. So here also order P square over M square. And the goal is to perform some sort of a matching between QCD and HQET. So for example, in QCD, I would have some diagrams. So PQ. So let us first focus on the this, on for example the case of heavy quark. So assume we are computing scattering amplitude. Assume scattering amplitude of a heavy quark in a static external potential. Yeah, I mean, in a potential A0. So this is my heavy quark. This is my heavy quark outgoing, and this is my external potential A0. So in this Lagrangian, the terms that would, just let me see. Yeah, the terms that would contain A0 potential are these electric fields, okay? The E is minus grad of A0. So this is the term that would contain the A0 part. This is also the term that contains the A0 part. This piece and this piece would contain my, this A vector. Sometimes we work in Coulomb gauge. So, but he,
External potential you refer to.
no, this is like, I mean, in general, for the loop calculations, we do sometimes Coulomb gauge for simplicity. Here for the tree level, it really does not that much matters. So, yeah, so in QCD, what you basically do is compute this diagram P, diagram Q, whose vertex is IG gamma dot A. U minus P. So you write this as I U bar P gamma dot GA U minus P UP. What happened? Oops. Jump ahead. Sorry. So I'm talking about A0. So A0. Yeah, sorry, my mistake. Gamma 0 G A0. Yeah. Sometimes in the literature, this diagram is also represented as this with this dotted line, okay? Just because the A0 part would be related to your 1 by R Coulomb potential eventually when we have a quark and an anti-quark. So just to make you aware, if some literature, basically they represent it as a dashed line. Sorry? It's a gluon here. I mean, this is QCD I'm talking about. Yeah, I mean, there is color indices. I'm not being very specific here. So there are TAIJs there. So yeah. I just want to show the basic, I mean, the TAIJ part on both the sides have to remain the same. So yeah, so U of P. Now if you do, if you use this expansion here for the spinners starting from the QCD, what you end up getting is something like is minus U dagger I'm skipping a lot of steps, but there would be steps in my notes, so I would maybe leave it at that point there. So basically, this is my QCD part. I wrote the amplitude. just did the non-relativistic expansion here, started with this, substituted it here, and this is the result that I get. In the HQET side, in HQET side, I would have one diagram, so which will just give me so anybody can tell me where this diagram is coming from the HQET Lagrangian? Exactly, correct. So this is the most simplest thing. You just expand this V dot D term and you get this A0 sitting inside in the hadron rest frame. So this is minus I U bar G A0 U minus PU. There are other set of diagrams coming. As I already told you, you have to first look at the HQET Lagrangian and see where the A0 will come from, instead of working through the whole Lagrangian. So I wrote the term corresponding to this. There would be this one that will give me A0, and then there is this one that would give me A0, nothing else. So there are three set of diagrams that I can immediately write. Then there is another diagram, which is again the same thing, but this is with I CD U dagger Q minus P square by 8M square. And then there is this third diagram. So this comes from CD H nu bar D dot GE by 8M square HP. And then there is third diagram in HQT, which will basically be again, so let me mark it as cross. This is more complicated, so this would give me something like, CS U dagger sigma dot Q cross P by 4M square GA0 Q minus P. And this is the diagram that comes from this D cross GE term. So now basically HQET is 1 plus 2 plus 3. So you sum up all these terms. And what you get is minus I U dagger GA0 Q minus P 1 minus CD with some coefficients P minus Q square over 8M square plus ICS something with 4M square piece. Or maybe let me just write it down then. Sigma dot Q cross P. So you have this HQET amplitude, you have this QCD amplitude. Maybe let me use two different colors. Okay, so I have this. And then I have this. Okay, you just compare one-to-one term. You immediately see some of the coefficients are 1 at tree level, which is what we are getting from the naive expansion also. And this immediately tells you that CD is 1 plus there would be some higher order alpha S corrections from the loop. CS is also 1 plus order alpha S corrections from some of them. So again, the goal of showing this matching calculation is to just to demonstrate to you that every time our goal is to have the IR matching same in both the theories. In loop case, there are these 1 by epsilon IR that sometimes comes from the loop calculations, and the 1 by epsilon IR from the full theory has to match with 1 by epsilon IR from the EFT. Epsilon UV part, either you cancel it through counter term or you absorb it inside through Wilson coefficients of the EFT. You will see one example, let's say in the exercise session Monday, So the one loop calculation where you might have to compute the anomalous dimensions for the CF coefficients in HQET. Okay, there would be diagrams there. So next, what is the time? We may take a break a bit. Yeah. So the next part, I would demonstrate the reparameterization invariance because that is to show the Lorentz invariance part. And then because I have shown you the HQET Lagrangian, I will explain the degrees of freedom in NRQED, write the Lagrangian. I think Professor Rishi might pick it up from the PNRQED part, or we will see whether we can describe, let's say, Rayleigh scattering in NRQED at some point later. So yeah, let's have a break a bit. Thank you.